The process begins with the preparation of carbon fiber sheets. A CNC machine precisely cuts the carbon fiber material into specific shapes and sizes required for the frame. Once cut, the carbon fiber pieces are layered strategically to achieve the desired strength, flexibility, and weight distribution. The carbon fiber layers are then laid onto an EPS expanded polystyrene molding. This mold acts as a structural core, helping to define the frame's shape and ensuring proper alignment of the carbon fiber layers. The next step involves wrapping the laid-up carbon fiber material around the EPS mold. A vacuum process is performed to remove any air pockets trapped within the carbon layers. This step ensures the resin is evenly distributed, enhancing the frame's structural integrity and eliminating voids that could compromise its strength. The wrapped and vacuum-sealed frame is subjected to heat treatment within a mold. Once the heat treatment is complete, the EPS mold is removed, leaving behind the hollow and lightweight carbon frame. This turn-out process reveals the raw frame, ready for further refinement. The frame undergoes precise machining to finalize its geometry and ensure compatibility with other bike components. Critical frame parts are bonded together with high-strength adhesives. The rear and front triangle sections of the frame undergo rigorous quality control checks to ensure they meet the design and performance standards. Any imperfections are identified and rectified at this stage. The frame is subjected to extensive fatigue testing to simulate the stresses of downhill racing. Impact tests are conducted to verify the frame's ability to absorb shocks and resist damage from sudden impacts, ensuring its durability in demanding conditions. Finally, the frame undergoes a meticulous painting process, giving it a sleek, professional finish. The paint not only enhances the bike's aesthetics, but also provides an additional layer of protection against environmental elements. The process begins with carbon laminate material, which arrives as pre-impregnated, prepreg sheets. These sheets consist of carbon fibers infused with a resin system, making them ready for molding. The material is supplied in unidirectional or woven fiber formats, depending on the design requirements of the wheel. The sheets are laid on a cutting table, where they are precisely cut into specific shapes using a vacuum system and a computer-controlled cutting machine. The vacuum table holds the material in place, ensuring clean and accurate cuts. The layup process is one of the most critical stages in the production of carbon wheels, as it directly impacts the wheel's structural integrity, weight, and overall performance. This step involves manually arranging pre-cut carbon fiber pieces onto a mold to form the rim's structure. The mold used for the layup is an aluminum core wrapped in latex. The latex serves two key purposes. It provides a smooth surface to prevent carbon fibers from slipping during the layup, and it helps compact the layers tightly for a more consistent and precise preform. The mold is divided into two sections, the male side and the female side of the rim. Using the pre-cut carbon fiber sheets from the earlier stage, the technicians strategically layer the material onto the latex core. Each layer of carbon is placed in a specific orientation to maximize strength in key areas while minimizing weight. For example, unidirectional fibers may be aligned along stress paths to handle loads efficiently, while woven fibers may be used to reinforce areas prone to impact or wear. During this process, attention to detail is paramount. Any misalignment or wrinkles in the fibers can compromise the final product's quality, leading to weak points or uneven performance. Once all the layers are applied, the preform is inspected for alignment and compactness. The molding process is where the carbon preform is transformed into a solid and seamless wheel rim. After the preform is prepared, the two halves of the rim are carefully aligned and joined together. A bladder, typically made of flexible material like silicone, is threaded through the center of the preform. This bladder plays a critical role in shaping the rim during the molding stage. The joined preform is then placed into a meticulously cleaned mold. The mold's cleanliness is essential to prevent contaminants from affecting the surface finish or structural integrity of the rim. Once the preform is positioned, the mold is closed and air pressure is applied to the bladder. The air pressure pushes the carbon fibers outward, ensuring they conform tightly to the mold's contours. Simultaneously, the mold is heated to activate the resin within the carbon fiber layers. The heat and pressure cure the resin, hardening the structure and creating a robust, lightweight rim with a precise, void-free shape. Drilling is a critical step to create precise holes for the spokes and nipples. This is done in a two-stage process. First, holes are drilled from the inside of the rim to allow access for the spokes. Next, additional holes are drilled from the outside to accommodate the nipples and provide seating for them. To prepare the rim for finishing, it undergoes a wet sanding process. This step smooths the surface and removes any imperfections, ensuring a clean base for applying decals and protective coatings. The sanding also helps achieve a polished appearance, which is essential for the high-end aesthetic expected by consumers. Quality control, QC, plays a vital role throughout the production process, with the rim undergoing several inspections after each step. At this stage, the rim is carefully weighed, and its surface is examined for any cosmetic defects. The assembly process begins with the integration of the hub and spokes into the rim. The hub is disassembled, and spokes are inserted before the hub is reassembled. Inserting spokes is a precise task that requires attention to detail. Each spoke must be inserted correctly to ensure even tension and alignment during the wheel building process. The spokes are threaded through the hub and attached to the rim via nipples, which are initially tightened halfway to prepare for tensioning. Balancing the spoke tension is a crucial step in building a high-performance wheel. Technicians apply Loctite to the nipples to secure them in place and begin adjusting the tension. They ensure that the wheel is true, which involves correcting any lateral, side-to-side, or radial up and down deviations. Balancing is achieved by listening to the tone of the plucked spokes, which indicates the tension. Uniform tension ensures the wheel is strong, durable, and capable of handling the forces encountered during riding. The final stage involves a thorough inspection of the completed wheel. Technicians perform a 46-point inspection that includes checking cosmetic finishes, measuring lateral and radial trueness, and verifying spoke tension. Each spoke's tension reading is recorded in a database under the wheel's serial number, providing a traceable record of its quality metrics. If the wheel passes inspection, it is packaged and prepared for shipment. This process ensures every wheel meets the high standards expected by cyclists, from casual riders to professional racers. The process begins with the design phase, where engineers develop the geometry and structure of the bicycle frame. Carbon fiber is chosen for its strength-to-weight ratio, and every detail of the frame's shape and layup is strategically planned. High modulus extreme HMX carbon fiber sheets are cut into precise shapes using robotic systems. This step minimizes material waste while ensuring accuracy for the complex geometries required. Over 220 individual pieces of carbon fiber are cut for a single frame. The cut pieces are then arranged into layers with specific orientations. The fibers are carefully aligned at angles such as 0 degrees, 20 degrees, and 45 degrees to provide the necessary strength and stiffness while saving weight. thicknesses are precisely controlled to maintain consistency across the frame. In the integrated molding process, IMP, the prepared carbon fiber layers are placed on a removable solid core with high precision. This step ensures that the layers are properly positioned to form a unified structure. The layered carbon fibers are then compressed and cured in a mold. This process combines heat and pressure to solidify the frame and create a single seamless structure. Unlike traditional tube-to-tube construction, this method eliminates joints and enhances structural integrity. Once molded, critical areas of the frame are machined to meet exact tolerances. This ensures that all components fit perfectly during assembly and that the final product is precise. The assembly process involves bonding the pre-formed parts and applying an additional carbon fiber layup in specific areas for added strength. At multiple stages of production, inspections are carried out to verify that the frame meets strict quality standards. Each frame undergoes rigorous testing to assess its strength, stiffness, and durability. Scott's testing standards exceed industry requirements, ensuring the highest level of reliability. The frame is masked and painted in a specially equipped facility with treated ventilation. Advanced enamels are used to achieve a durable and vibrant finish that resists wear and tear. Decals are applied by hand for precise placement, and a protective clear coat is added to safeguard the finish. This step ensures a polished and professional appearance. Each frame is assigned a serial number for traceability and undergoes a final inspection before being packed for shipping. This guarantees that the product delivered to the customer is of the highest quality. The manufacturing of carbon fiber wheels involves a meticulous and highly detailed process, ensuring the final product achieves the desired performance, durability, and precision. The process begins with the precise cutting of carbon sheets into required segments. These segments are tailored for specific functions, particularly to reinforce the spoke hole area. The cutting phase is critical to ensure that each piece fits seamlessly into the rim's overall design and contributes to its strength and performance. The initial layers involve a 3K weave to reinforce the spoke holes, followed by several additional layers for added strength and performance. Heat is applied to soften the resin, allowing the layers to bond as the tire bed foundation is formed. External layers are smoothed and built up to form the sidewalls and rim face. These layers are then wrapped to prevent slippage before the rim is placed in a mold. High-pressure molding is performed using silicone air bladders, which allow for double the pressure of standard methods. After molding, the rims undergo surface preparation. This involves cleaning, degreasing, and a meticulous inspection in a controlled environment. Artwork and decals are applied by hand, ensuring precision and alignment. The rims are then dried at low temperatures to secure the finish, followed by a light clear coat for protection. After curing in an oven, the rims are inspected once more for quality assurance. The wheel building process begins with the assembly of the prepared rims into complete wheels. This step requires expertise, as skilled workers, many with over a decade of experience, calibrate spoke tension meters and ensure accurate assembly. Spokes are fitted with utmost care, utilizing a proprietary tool that tightens them in 3 stages. This approach prepares the wheel for final tensioning while ensuring proper alignment. Nipples are lubricated with heavy oil to facilitate smooth movement and clean seating. In the spoke seating stage, rubber rollers press against the spokes to bed them into place. Hydraulic presses further seat the spokes, a process repeated a minimum of 6 times for every wheel. This ensures the spokes are firmly embedded, enhancing the wheel's stability and performance. Every wheel undergoes rigorous testing to ensure durability. Prite employs a machine known as the Beast to replicate road conditions, subjecting wheels to direct loads of 90 kilograms and lateral loads of over 150 kilograms. These tests simulate 10,000 kilometers of riding within a week, ensuring the wheel's structural integrity and longevity. Given the critical role of braking performance in wheel safety, extensive brake testing is conducted. Using Swiss stop brake pads, renowned for their superior heat management and braking efficiency, the wheels are subjected to sudden stop tests and long-duration braking simulations. These tests are designed to push the wheels beyond real-life scenarios, ensuring reliability under extreme conditions. A separate long-duration test evaluates the wheel's response to sustained braking pressure and high temperatures. By increasing the speed and applying constant weight, this test identifies potential failures and ensures the brake surface can handle prolonged use without compromising performance. The process starts in the loom room, where raw carbon thread is transformed into composite sheets. Carbon fiber, known for its exceptional strength-to-weight ratio, is the core material used in Giant's bike frames. In this room, spools of carbon thread are fed into automated weaving machines. These machines intricately interlace the threads, creating sheets of carbon composite material with specific fiber orientations designed to optimize strength and flexibility. This step is crucial because the alignment of the fibers directly impacts the performance characteristics of the final frame. From the loom room, the composite sheets move to the layup room, where they are meticulously cut, ordered, and layered into soft frames. Over 500 individual composite swatches are crafted, each tailored to fit a specific section of the bike frame. This labor-intensive process involves a combination of machine precision and human expertise. Highly skilled technicians carefully position these swatches in a precise sequence, creating a multi-layered structure. This layering process is key to tuning the frame's properties, such as rigidity, strength, and weight distribution. The soft frames, while retaining flexibility at this stage, are structurally formed and ready for molding. This stage demands incredible attention to detail and expertise to ensure that each frame meets Giant's stringent standards. Every swatch placement is recorded and inspected, as even the smallest deviation can affect the frame's integrity and performance. The soft frames then proceed to the molding stage, where they take on their final shape and structural integrity. Each frame is positioned into a steel mold, which is designed to match the exact specifications of the bike model being produced. Once placed in the mold, the frame undergoes a high-temperature, high-pressure molding process. The combination of heat and pressure cures the composite material, solidifying the layers into a single, cohesive structure. This process not only shapes the frame but also enhances its strength and durability. The precision of the molding process ensures that each frame meets exacting tolerances, ensuring consistent performance and reliability. After molding, the frames are removed from the molds and subjected to thorough inspections. These checks ensure that there are no imperfections or weak points in the structure before the frames proceed to the finishing stages. The final stage in the manufacturing process takes place in the finishing and painting rooms. Here, the molded frames are carefully hand-sanded to achieve a smooth surface, free from any imperfections or rough edges. This step is essential for both aesthetics and aerodynamics, as a sleek surface minimizes drag. Once sanded, the frames move to the painting section, where they receive their distinct colors and designs. Giant offers a wide range of finishes, from bold and vibrant colors to subtle, understated tones. Skilled painters apply multiple layers of paint to achieve a flawless finish. Stickers and decals are then added to showcase the giant brand and model details. Finally, the frames are clear-coated to protect the paint and enhance durability.